Okay, anybody has any question? Right, just to again reminder that next Monday, I'm not Monday, next Tuesday we have the exam and no class on the Tuesday, right? And project is due on next Thursday, right? Okay, then let's continue from the previous lecture. So we talk about beam bending problem. So beam bending is a little different from the previous problem because this is the C1 continuity. So we have both displacement and slope continuity there. And then now we talk about also two-dimensional or three-dimensional structure. So last time we talked about in particular 2D truss structure, and truss structure is truss structure consists of two force member only. Otherwise, not going to be a truss structure. So the typical truss structure has only pin joint, and the load is applied only at the pin joint, not anything else. Okay. So to solve that problem, what he did was that to develop the element, final element for each, oriented the member, truss member. So truss member is axial member, no bending, so only axial member like the linear spring. But now in terms of 2D, we have to look at the displacement both x and y direction. So we arbitrarily expand this one to x and y direction. So both displacement u and v. U is displacement in the x direction, and y is displacement in the v is the displacement in the y direction. And then, so you see a lot of zeros, which has no particular meaning in this matrix itself. But what it did was that in the next slide that we like to have coordinate transformation. So coordinate transformation from between the global and local. So local is going to be the orientation of the member itself. So local is continuously changing depending on the orientation of member. But global is going to be our reference. The reason is that even you have a changing orientation of member, we like to establish that in terms of global x and global y, then now we can do proper summation of the matrix in terms of the global coordinate system. So this is the relationship between the local and global, and C was cosine of this beta, and S is going to be sine beta. So beta is defined counterclockwise positive, okay? As usual, this is positive. So if you go the other way, then that's going to be negative. And then from energy principle, so that the total energy, energy is going to be 1/2 displacement times spring coefficient, stiffness matrix times displacement. From there, substitution of the local displacement by the global displacement of the transformation equation. Then eventually we express that transform matrix, stiffness matrix in terms of global coordinate system shown in this way. And then our degree of freedom is going to be expressed in terms of global coordinate system. Then once you do that, then we can now add them up together to find the system matrix. So that's what we did in this example here. So again, going back to the same example shown in the one of prior slide. So look at 3 elements, A, B, C, and we have a node 1, 2, 3. Then for each element, for example, element A, you have to establish your local coordinate system. So you have a choice of local coordinate system going 1 to 2 or 2 to 1. Either one is perfectly fine. But if you go 1 to 2, then angle is going to be 0. If you go to 2 to 1, then angle is going to be 180 degrees. So if you plug that into the previous expression in here, to calculate cosine and sine of the angle, then you come up with the stiffness matrix in terms of global coordinate system for element number 1 element number 2 is, again, if you pick this way from 2 to 3, that's going to be 60 degree. So you calculate that. And finally, the last element also, in here, we select the local coordinate 1 to 3. 1 to 3 means from here, 1 to 3 means this angle is going to be 60 degree. So pi over 3 is 60 degree. Then cosine, sine of 60 degree shown here. And then this is your global matrix. I mean, the matrix in terms of global coordinate system. Then assemble them, 3 matrices together, then you'll get the global matrix. Okay, system matrix. Then the size of system matrix is going to be 6 by 6 because this one, you have 3 nodes. Each node has 2 degrees of freedom. So the system matrix is going to be 6 by 6. And also we talk about the boundary condition. So here, displacement are 0, both x and y direction, but force are unknown, both x and y direction. Here, displacement is 0 in the y direction, but force is going to be 0 in the x direction because nothing is applied here. And at node 3, force in the x direction is equal to p, force in the y direction is going to be 0, and displacement are unknown. So then you solve the equation to find the displacement and the reaction forces at each nodal point. So this problem is, if you solve that using finite resolution technique, as I mentioned last time too, since we are solving both static equilibrium as well as the formation condition, so we find not only the nodal forces at the nodal point at the pin joint, but also we look at the deformation of the shape, how this triangular shape is going to deform because of applied load. We can find all those displacement. And if you do this one just statics, okay, from method of joint and method of section, then you only get the reaction forces at the joint, but not the actual displacement. Okay, so this has some kind of advantage of getting both information. That's what we talked about last Thursday. So today we want to now continue to talk about the 2D frame, not the truss, but frame. So what is the difference of frame? So to illustrate the example of frame, this is going to be inverted L shape of the frame, like a bracket. So fixed at A, and then force is applied at the tip at C, applied force here. Then to illustrate why this is a frame, you just draw free body diagram. You draw free body diagram, member AB and member BC. Then from static, looking at member BC first, this is applied force, this is applied force. Then to maintain equilibrium, summation of force and summation of moment, then force have to be same magnitude in opposite direction, right? Opposite direction. So it makes sense. Summation of force in the y direction, vertical direction is 0, and there's no force in the x direction, so we don't have to worry about it. But also we have to maintain the moment equilibrium. So if you take a moment about that point, the length is L. So you got P times L, then moment. So you have to cancel out that. So you got a moment have to be P times L here. So that's complete free body diagram and apply force and moment. Then on this member, from Newton's third law, action and reaction, if P is going to be upward here, then this P is going to be downward. Same magnitude, opposite direction, so they cancel out when they put together. Likewise, moment is the counterclockwise, then that's going to be clockwise. So they cancel out each other. So once you draw this free body diagram, then you can see that both of them, of course, you can put reaction forces on this side too, like this, and then the moment like that. Huh? But anyhow, if you look at each member, then the member is not a two-force member. In other words, that you have only forces applied at two locations. No. This case, you have not only forces, but also the moment. Same thing in here. You have forces, but also moment. So it's not a two-force member. That means the member is going to have a bending action. Okay, so this is going to be a frame structure. Then next question is, how do you analyze this frame structure using the finite element solution technique? How do you do that?
Professor,
Yes.
I'm having a little bit of trouble seeing this green.
By the way, can you, dim the light a little bit? So,
You're saying that there's a moment being applied on the beam, which is that one in the middle image there.
this one?
Yeah, that one.
Uh-huh.
Okay, so that's not a reaction.
So that is from Newton's third law, action, reaction,
Oh,
right? So in other words, when you put together, they cancel out nothing in here. All right, then how do you, construct the element matrix for this kind of frame element? So if you look at frame element, what do you see? This force P in this member, vertical member, we call this the column. Somehow we differentiate this is column, this is beam, but doesn't matter. Both of them basically the same type of structural element. So here you see that you have a P which act as a axial force. So member subject axial force and bending moment. But if you look at this member, you got the shear force and bending moment. So in other words, beam bending element for frame element, you have to represent both axial force, shear force, and bending moment. You should be able to do that. How do I do that? At least if this is going to be linear elastic, you know what linear elastic means, right? If you don't know, let me know, or you can ask me later too. It's up to you, but linear elastic, then what we do is we combine two elements. So you got stiffness matrix for this thrust element, one-dimensional thrust element, and you got the stiffness matrix for one-dimensional beam element. Then thrust element has displacement along the axial direction, and beam element has displacement in the transverse direction as well as slope. That means that represents the shear force and bending moment, and that represents basically axial force. So if you put together this matrix and then matrix, so like that, right? Then that's going to be the frame element, as long as the element is going to be along the horizontal direction. So in other words, you simply add this matrix, then matrix, impose to each other, then this like this. U1, V1, theta 1, U2, V2, theta 2. So this is U1, V1, theta 1, U2, V2, theta 2, right? So if you look at these four components, of course, including that, those four components come from the stiffness matrix of, where is it? If you apply this one, this element give you this stiffness matrix, okay? And this beam element give you this stiffness matrix, 4x4. And this one and that one are independent, so that you got zero. So they are independent. This degree of freedom and that degree of freedom, linear elastic problem, they are independent. So you got all zero. And all together, this is 6x6 matrix because of that 6 degree of freedom per element. So at least this is for the stiffness matrix of this element. But in frame structure, again, element orientation is going to be arbitrary. It doesn't have to be, everything is going to be horizontal. So in this case, we have to do also same kind of coordinate transformation between global, and local. So this is global. Again, I'll put bar here. U1 bar, V1 bar, global, and local is going to be U1 and V1, shown in here more clearly. X bar, U bar, Y bar, V bar, this is global. And this is local. Okay, like a truss structure. But I have a 6 degree of freedom because I have a 3 degree of freedom per node. 3 degree of freedom per node. Right? Previously, we had 4 degree of freedom in a truss structure. But this is 6 degree of freedom because you have also slope here. Then what is the coordinate transformation for that one? In terms of U and V, or U bar and V bar, in terms of displacement, they are exactly same as before. This is exactly the same as before because what we derive for the truss structure, we derive for the truss structure, which was in here. You know, when you developed the truss structure last time, this is exactly same for the frame structure too. Okay, the frame structure too. Then what else? This element has rotation or slope. So slope is about the z-axis. This is the slope. Okay, about the z-axis. So the slope is the same whether you look at in terms of global coordinate system or local coordinate system, because both of them is about the rotation about the z-axis. That's the slope. Okay. So in other words, what it means is that this is going to be 1. So what does it mean? Global, slope in the global coordinate system is equal to slope in the local coordinate system. No difference. Okay. So that's going to be 1. So this is also transformation matrix 6 by 6 in terms of local and global for the frame element, 2-dimensional frame element. So if you apply the same energy, concept we did for the truss structure, then this is going to be same as before. Global stiffness matrix in global coordinate system is T transformation matrix transpose times local stiffness matrix multiplied by T. So this is all 6 by 6. 6 by 6, 6 by 6, and 6 by 6. So if you do this multiplication, you come up with now this expression. So this expression is A1 to A2, A3, A4 is, shown in here. So a little more complex, but not that very difficult. I mean, so this indicates that how much, contribution between axial component and then bending component. So that it means in this term because of the orientation of that. So that's kind of coupled between the axial force and the bending moment in here. So anyhow, this is going to be 6 by 6 matrix. So if you go back to the example we talk about in here, in this example, if you're going to analyze this example here, then if I say this is going to be node 1, 2, 3, let's say 1, 2, 3, I'm going to use just 2 elements, A and B. Then 1, 2, if I say this is going to be my local coordinate system, then angle beta is going to be 90 degrees. So you have to calculate, cosine 90, which is going to be 0, and sine 90 is going to be 1. So you calculate all of them for this matrix. And then for element B, if I take this as my local coordinate system, then angle is going to be 0. So that means this is going to be same as the original matrix we developed in previous section. Where is it? In here. It's going to be equal to that. It's equal to that when angle is going to be 0 degree. And then we can assemble them together. And the boundary condition here, displacement 0, both x and y, as well as slope is 0, right? And that point, the forces and moment are 0, because there's no force moment applied at that point. And at that point, force in the x direction is 0, force in the y direction is going to be negative p, and the moment is going to be 0. So you can apply that to solve this equation for this example. Any question? Then you can do same thing for 3D truss and 3D frame element. So we are not going to, do that, just a little more, extra calculation, but concept is same. For example, if you have frame, right, then you got displacement. Displacement is going to be same, like u1 and u2 along the member direction. But now transverse direction, you have two components, V1 or V2. So in other words, if this is the member, U is going to be this, and V1 is going to be this, and V2 is going to be there. Okay, true. And also you have corresponding the moment, this way rotation, and also about this one too. So you got two different rotation. In other words, one is slope like this, slope like this. The other is slope like that. Okay. So you have those degree of freedom, and then also this one could have twisting. Three-dimensional member, you can have twisting like that, twisting moment, right? So you got U, V, let's say Ux, Vy, and Vz, and then you got theta X, theta Y, and theta Z. So this is in plane displacement, axial direction. Those are two transverse displacement. And this is going to be the angle of rotation. And those are two slopes due to bending. So you got now six degree of freedom for each nodal point. That means if you have element of the two node, you have K matrix going to be 6 plus 6, so 12 by 12. Okay. Then you can do similar coordinate transformation from local to global coordinate system. So you can get the stiffness matrix in terms of the global coordinate system. So all of them are in the textbook. So I'm not going to go too much detail in here. However, one interesting and important thing in here that especially for 3D, we got a torsion. You got a torsion. So when you have a torsion, if you have a circular member, then you have a very nice equation for torsion. We learned that in chapter 4, right? For torsion. So you can construct the stiffness matrix for torsion without any difficulty for that one. But if you happen to have, for example, non-circular shape, right? If you have non-circular shape, then we don't have such a simple equation for torsion. All right? So people have to do some kind of approximation or something different, but it's not as straightforward as like that one for a truss structure for that one. Because this one, we have warping of the geometry, right? This one doesn't have any warping. This one has warping. So that when you look at the 3D frame structure, and then cross-section is not circular, then you have to be a little bit careful, because what is going to be the stiffness matrix for that geometry. Okay, so people develop some kind of equivalent stiffness matrix like this, same kind of format for this one. But of course, that is an approximation. That's not the precise. So you have to understand the limitation too. Okay, that's the end of chapter 8. Any question up to this point? So, one question. You have a truss element and you have a frame element. Now, can I use frame element to solve truss structure or vice versa? In other words, the example we talk about here, truss structure, frame structure, right? And I'm going to use the frame element, 2D frame element to solve that up. And I'm going to use 2D truss element to solve this one. Does it work? No? What do you think? Does it work?
Yeah.
Let's do one by one. This one first. Is that okay? Or not okay?
I think that the truss, the
The-
frame
the-
elements take the moment into account,
Mhm.
and the truss ones didn't. So I know definitely that you can't use the truss element on the frame, but the frame element on the truss, I don't know.
So for this one, let's look at that one. So this one, the frame element has not only axial force, but also transverse deflection or shear force and bending moment, right? But this one doesn't have that, correct? So in other words, frame element has additional capability to represent additional different kind of load for the structure. So bottom line is those additional the capability, if you do not use it, then it's okay. In other words, this is much bigger set of potential solution, and this is going to be a small part of that one. So truss is going to be a small part of that, the frame, the structure. But you have to make sure that, for example, there is no moment in here, so you have to apply those boundary conditions properly. Okay. Otherwise, if you do not apply the moment bound condition in here, then your matrix could be singular. So every moment have to be 0 in every node because this doesn't have any moment. So you have to clearly, constrain that kind of motion. So bottom line is, if you use frame element for that one, it is okay as long as you properly apply those kind of additional constraints. Now the second part here, this is the frame, but I'm going to use truss element, then this is not acceptable because we cannot represent the bending action, slope and moment. So that's not acceptable. Okay? Make sense? All right, then let's take a short break and then start the new chapter.